Let me go to back to this picture. I keep coming back. Um, so that is the whole topic is here, and the idea is that we started with the mass of a rod of non-uniform density, okay, and then we understood the mass as the integral under this as the integral of the density function, and therefore the area under the graph of the density function, which is the one on the right. Okay, and then furthermore, we took it beyond that. We also answered the same question about different question about the same thing, and that is where's the center of mass. But it's still the connection is there, and the connection then is going this way, like this. But you can go backwards as well. So let me illustrate that. So remember this. So that's the graph is supposed to represent the piece of paper, fairly firm. Supposed to represent the area under the graph, more or less, so it is uniformly, this density is uniform, okay, and so the mass of the rod is equal to the mass of this thing, okay. So you go from non-uniform to uniform, but shape simple, shape complicated, okay, so that's the trade-off. So how do you go back from this to a non-uniform density? What should I do with it to get something of non-uniform density? I could try to roll it if I could, like this. Okay, so I take it and roll it like this. Okay, so then it becomes one-dimensional again, like a rod, but because there is more paper here, has non-uniform density. Okay, so the density function of this is that, and vice versa. I can go back and roll it together into one. Another way to think about it's like where there is more material in the rod than when you spread it out, like with some kind of a knife on the table. Say it will go farther. Okay, so that's the idea that how you can see it in practical terms, which is it is a mathematics, but you can also visualize it. So, which is what my comment was about. Okay, now the formulas are certainly very convenient, and we have now two that are to be used whenever appropriate, depending on the circumstances. Either you have a specific data in the form of a spreadsheet or something similar to that, and then you apply the summation formula here. Summation formula, well, actually we have two summation formulas. This is the one in terms of the densities, the one that we carried out last time with the data spread out through the rod, and then we computed its mass, and we computed its center of mass as well. Okay, so and that's where this came from. Okay, and then but if you're doing something more theoretical, then the density is given by a function which you may have made up or derived from some theory about what's going on, and then you have to integrate. Okay, so the latter is certainly slightly more challenging, but not really by that much. So like I said, it's still applicable, that the definition is still applicable to this situation, and that is the denominator is the mass, the total mass of the rod, and while the denominator is the total moment. The total moment of the rod relative to the to 0. Okay. Okay, so we'll get back to both of these, and carry out some computations. What I started talking about yesterday was this: beyond physics. Here it is. Beyond physics, where does it take us? And it takes us to what amounts to data. Okay, so we don't have to deal with anything physical, nor do we have to limit ourselves to dimension 1. But the idea of the center of masses has wider applications. So as you can see here, we have possibly the same person or the same gun shooting at the target. The pattern is different. And then you ask yourself, what is the difference? And the difference is probably the sights. So the latter might have misaligned sights. So that then you might ask yourself, by how much? And that is where will be looking for the center of mass. So the center of mass for the former, it is almost in the center. It appears. I mean, if you start thinking about it, it will be almost in the center. And then for the second one, it's clearly off. Okay, so of course, what is the center of mass is something that we already know. So it's something that is now not a rod, but a two-dimensional object. I could still balance it not on the way we did last time on a ridge, but rather still on a single point. And frankly, where is it? I only know that this is half circle. Okay, so if I should put my finger somewhere on this radius halfway because of the symmetry, right? So it should be here somewhere. But how far it goes towards the edge as opposed to the arch is unclear. I know that I should be closer to the diameter rather than to the center. So it's not so easy actually. Well, something like this. Okay, so that little bird that I had yesterday was easy to balance because it's designed to be balanced, and anything like this requires actual computation. So we might do that, but the point is that how we are translating that understanding of center of mass from dimension 1 rods and to high dimensions and beyond anything that necessarily is physical. So for example, the question is that how do we evaluate not the accuracy of our shooting, because that is done. You just count the number of well, how do you I suppose. Well, that's how you would evaluate accuracy. You would count the number of tens, nines, eights, and so on, and that will give you the idea of how well you've been shooting. But what it gives you the frequency of your of these possible events. And then you count. For example, if I take here, well, presumably this is 10, 9, 10, 9, 8. Okay, so 10, 9, 8, and so only 3 numbers will give you. So I'll have, it appears to be, I'll have like a. This is what I'm going to have. Okay, it's not working. I will have, I'll count the number of times everything has happened. So I'll have 10. I'll have how many 10s, how many 9s, how many 8s, and it appears I have 1 10. I have, let's say, 6 9s, and I have 3 8s. Okay, so that tells you the accuracy, but it is really not good enough because I could try carry out a similar construction for the second target, and what I have here, it is disproportional, frankly, but so I have actually because the size of the bullseye is different, unfortunately. Yeah. Okay. Well. So well. Maybe I'll do it like this in order this to be comparable. So this is 9, this is 8, and this is 7. So then I have 1 10, I have 2 9s, and I have 8s. How many 8s? I have a bunch of them. Well, let's say 7 or so. Okay, so there are two different distributions that they don't really they only tell you how far from the center you are. They don't tell you which way you skew, which way your gun is misaligned. So you can see you're shooting low left on the second image. So you have to evaluate, not only you have to automatically way to figure out where it is, but also how far. So, and that is the answer. The answer is you take this as if imagine that these are weights, okay? And taken together, I would be looking for a place where that the weight's not the target obviously itself, but imagine that every shot is worth I don't know, 1 pound, and you place on a piece some piece, say piece of plywood, and you place 1 pound weight on each of the place where you hit the target, and then you try to find where it balances. Okay, and where it balances will be your average, or rather expected value of your shot. So that will be, for example, if you think about it, probably for the first one, the center of mass for those holes, if you put it once again 1 pound on each, will be very close to the center, probably a little bit to the left, but pretty much here. That is roughly where the center of mass is, and it is fair. That would be a fair assessment of what's going on. On the other hand, for the second image, the center of mass of your shots will be somewhere maybe here on the border between 8 and 9, and yeah, somewhere in that area. And not only that, it's on the border of 8 and 9. It will be lower left. Okay, so you'll know that I don't know, 1 inch away from the bullseye is how far your sights are misaligned, how much they misalign, and then you'll find it through this. And then once you go that way, you realize that we're talking about data, and it doesn't have to be a target; it could be anything else. So you collect any kind of data, and then you ask yourself what to expect next, and then that is exactly what's called the expected value. Studied in classes on probability and statistics. That's where it comes from, and that's what calculus gives to probability and statistics, is the ability to handle things like that, and it's a very basic idea of what is the expected value. So you have collected some data, some statistics about a certain random event, which however might have some pattern. Okay, so how do you see that pattern? That's how you don't want to see that. You cannot visualize it frequently. If the dimension is beyond say 2, it's hard to visualize. So how do you do it? You do algebra. What is it exactly? You find the center of mass of the data. Okay, and then that will be your expected value. Expected performance of I don't know, stock or something like that, or a combination of stocks, depending on the circumstance. What to expect, or in other words, what has happened on average. Where is the average shot? Where is the average shot? And that's the center of mass gives you the average shot. So later on, we'll do the two-dimensional thing. So we'll stick to, for the most part, to the one-dimensional thing here, but at least we could solve some problems of this matter. For example, it would not be practical ones. It would be possible for us to find the actual center of mass of such a thing as a half a circle. I think it is more or less close to the truth. Okay, so let's figure it out. There's a certain challenge here, because we are only able to look at the picture at the bottom, even though I can represent this circle with a formula, right? So we know the formula for it. The challenge, we're going to only get the bottom, right? The center of mass this way. Okay, so and we know what the answer is. Let me point it out, as I pointed out last time, that half a circle, right, where is the center of mass? Okay, and well, the answer is kind of obvious if you're only talking about the x-axis, but rather than, I mean, this, if you look at this picture, then you know what it is. It is a physical object of a certain shape, and there is no function. There is no function to talk about. So it is the next step is how do we figure it out? We put it on the xy plane, appropriately located. The simplest place to put it is to put it naturally as we have before, like this. So suppose it's from -1 to 1, so this is my object. Okay, so then we can compute the mass, and we don't have to integrate anymore. We did it once, so we know that the mass will be, that's helpful. It is, in fact, what is it, pi over 2, right? So that's our mass already. We carried out that integration previously. But furthermore now, and well, let's do it anyway. Let's demonstrate that the center of mass, horizontal-wise, will be at the center. So our C is, according to the formula we just saw, this is the formula. Well, how do we do it? We divide the total moment over the total mass, and we already have a total mass, so we just need the numerator. So let me do the numerator. So the total mass has been found. Well, you don't even have to say total. I mean, under the circumstances, it's all total. So I just talking about the whole thing in the moment. Moment is the integral from -1 to 1 of what? Of our density function, or well, density function, or simply the function that gives me the top edge. Okay. So I keep asking this question. So the formula of this one is of the top edge of the circle. That should come quick. Minus x squared. Thank you. Okay, so so that is what I'm going to be integrating. That's my L. But then there is an extra x. So let me actually make it clear that to put these two side by side. So I know that the answer is pi over 2, but let me write it as an integral anyway. So it will be between -1 and 1, 1 minus x squared dx. And we carried out this computation. The answer is pi over 2. Now we're doing the same thing, but there is an extra x. There is an extra x here, so then the answer is to be determined. So it's integral between -1 still, 1 minus x squared still, dx still, and then in the middle there is an x here. Okay? Incidentally, so you might remember how, well, do you remember how we found that integral, the first one? The first one, how did we find the first integral? Substitution, trig substitution. Okay, so it might be then tempting to apply the same technique for the second. But there is an easy way. How do we compute this one? Well, trig substitutions are tricky, were tricky because they were going against the pattern. And the pattern was every time you say composition, choose what's inside of the function, the first function as your new variable. And that's the standard use substitution, as it's called sometimes. So in fact, the first one was hard. The second one is easy because we simply take 1 minus x squared as our new variable. Okay. Why is it going to work out? Because that extra x is actually helpful. It makes things longer and seemingly harder, but actually it's simpler because x is the derivative of, well, as we're going to see in a moment. So if this is my u, then I have d, so u is equal to 1 minus x squared, u du is equal to negative 2x dx. So as you can see, that's where my x will be helping us to cancel things out. So dx is equal to, in fact, negative du over 2x. And if I actually carry out the substitution, what I'm going to get is integral from -1 to 1. This is still x, however. And here I have square root of u. I have x. And I have negative du over 2x. x cancels out, and I'm left with only u's. So integral square root of u negative 1/2 du. From negative 1 to 1, this is 4x's, still 4x's. So what's the integral of square root of u? What do we do with the square? I mean, you just well, what's the formula we apply? The formula? What is square root? Right. So u square root of u is u 1/2. So when you integrate by the power formula, the power goes up. So I have u 3/2 divided by 3/2. Okay. I want to switch to u's here for my limits. Okay, so x is equal to negative 1, x equal to negative 1, then u is 0. Right? So look at my formula over there at the top over here. U is equal to, my substitution is u equal 1 minus x squared. So if I carry out my integration correctly, now I have substitutions finished. I have my antiderivative in terms of u, but then if I need my definite integral, so I have to have my limits in terms of u. So what I do, I simply substitute. So x is equal to 1, then u is equal to 0, right? U is equal to 1 minus x squared. So, okay, 1 minus x squared. What about the other one? It's also 0. What does it tell you? Well, the answer is 0. So the moment with respect to the origin is 0 of this object. So what's the conclusion about the center of mass?
It's at the origin.
It's the origin. It's 0. So indeed I could put my support right here, and it will balance. So let me try. So here somewhere. Yeah. So I certainly have no chance of balancing it like this. But if I put it on the edge, maybe, well, let me see if I can balance it like this. Yeah, pretty close. So I followed that line over here that I've cut in half, and as expected, I have exact same shape to the left and to the right of my ridge, and then it balances, right? So you can certainly see that. In fact, you can look at it like this. Every time this slice is balanced here, that slice is balanced here as well, and so the whole thing is balanced as well. If I put it this way, the problem is that is not. This is a whole ridge, so I'm balancing it on a ridge. I want to balance it on a single point, the way we would balance anything. Okay, actually there's an important point why we care about center of mass. It is motion, right? So if you remember calculus 1, you can study motion. You throw an object and it follows a parabola, right? Remember that? You have gravity, and you can tell how it follows. You can see how it goes. But that's only one thing. What else is going to happen when I throw it? In addition to just flowing across the room. Yeah. It's going to rotate. It is unlikely to go like this. This is very unlikely throw. You have to be really try hard for the object to fly like that. It will rotate, probably likely. So how, around what point? And the answer is it will rotate around the center of mass. Okay, so any kind of more complex motion beyond. So calculus 1 will give you the trajectory. And then calculus 2, you need calculus 2 in order to understand something on the next level, and that is whatever is happening to the object. Apart from its motion, there is a motion with respect to its own central mass. Okay, so that's why we care. Any kind of motion requires then study of knowing where the center of mass is to begin with. Okay, so and that's why we are not happy with our answer just yet, because we only have one. That's not the center of mass. The center of mass should be, we can guess. It is, as we have established, it should be here somewhere on the axis. But then the actual center of mass of one single point location should be here somewhere, possibly. Somewhat close to the x-axis, but on the center of the half semicircle, but closer to the edge. So how do we find it? We don't have that information just yet. So well, it is possible to figure out, well, what I'm talking about of finding is this. We need another axis, so kind of another point of view. So we did the x-axis, and now we just need to do the y-axis. And we'll have in a similar fashion, we're going to find, like that triangle I put there over there, that will support the horizontal. And now there will be something like supporting the vertical, even though I can't put it like this, probably. Well, maybe not. But the idea is the same, so we just need to find what amounts to the moment relative to the x-axis. So this was the moment relative to 0, but it's the same as to say that it is relative to the y-axis. Okay, so how much tip we have relative to the y-axis. Okay, so and they just happen to be 0, but in general you can imagine wherever you can place it elsewhere. And the way we have done it, the moment is once again the sum of all the moment of every object times the leverage. The formula is well, that's the starting point, and the formula, the balance formula is here. So the balance equation. Okay, so mass times the lever. So, but this one is done with respect to x. Why not to do it with respect to y? That would be very similar. There's no difference whatsoever. So we have masses distributed, and now this time they are distributed on the plane, and just we're looking at what's happening relative to the y-axis. So the masses will be the same, but instead of the looking at the x-coordinates, we'll be looking at the y-coordinates. So, but the idea is the same. So let me try to do that. So we'll get back to this. But right now what I want to look at is this. So once again we have our seesaw, and we place a few objects of different sizes. Maybe. Like this. So now the idea is, we suppose we already know that, or we don't care at this point where the support is, but now we are not concerned with that. We are trying to do something else, but rather this is what I'm looking for. So I, rather than having a seesaw, well the seesaw idea is kind of we're done with it. I'm looking at it like this. So one object still made of those little squares of each of single weight, right? Okay, so it's made, that is my object. It looks like this, and I want to balance it. So I already suppose I might be able to balance like this, but what I'm really after is now I want to balance it on the horizontal edge. Okay, so in other words, it should be, I can't tell exactly, but it should be here. The axis should be here somewhere, probably. Okay, so if I put my support of kind of this kind of thing, support, then it should be balanced. Okay? So it is still a function. You can still think of this as a function y equal f of x. Right? So this is still the x-axis, that's still the y-axis. And then now, so it's still area under the graph of the function, and I might try to figure out what is the center of mass. I don't need the mass anymore. We know what it is. I need the center of mass. Okay, so y equal f of x is the upper edge of my graph. Okay, and so let's try to figure out what the moments are relative to. Well, let's say instead of having x equals c, remember that one when we went vertically, we have maybe say y equal d. Y equal d is our straight line with respect to which we're going to be balancing our object. Okay, so then it still applies. The idea still applies. So the region is balanced when the total moment with respect to y equal d is 0. Okay, so that's the same thing. Total moment with respect to 0 is with respect to y equal d is 0. So what does it mean? It means we're going to be measuring our so masses are, we know what masses are, they're the same, but what changes is how we're going to measure the levers, and this is how we're going to measure the lever. For example, if I take that upper triangle over here, say this is my triangle, let's say my triangle, no, rectangle, then this is my lever. This is my lever is this. Okay, so we used to do it horizontally, and we ended up with our formula, the formula that we just started with today, and how we're measuring vertically. Okay, so how does it work out? Let's try to figure out what this is. Let me write out the that statement over here in the form of a formula. So it will be sum mi yi minus d equal to 0. So it's the same story. Like I said, the total moment, total refers to the summation, and the mi and what follows. What are we adding up? Are moments, and moments are mass times the lever. Okay, so the lever once again is just is done by subtraction. Okay, so now well, we can carry it out. Well, let's carry it out. This plan with Excel. Okay, so we'll take a look again at what we did last time. This one to refresh our memory. Okay, so not this, but rather that. Okay. So as you can see, so forget about the rod. That's where we started with the rod. So we don't really care about the rod anymore. So let me, if it is possible to clear rules. Okay, there it is. So there is no raw. I thought I did. Okay, let me try again. Remove. Clear. Clear rules. Okay, so remember we started with the rod, but now we switched gears, and now we're dealing with the object that has a uniform density, but it has as the shape. This is the shape. Okay, so certainly we were going to be dealing with the circle, but that's a starting point. So let's just refresh our memory about what we did. Okay, so coordinates, now densities are gone, so it's not densities but rather heights. Okay, so literally what we see the picture of is our object that we balanced. Okay, and coordinates of what? Of the slices, of how we sliced it. Then, like I said, instead of having a density, we have height, so the height matters. And then then we computed the weight of each, which is what happens to be what? It's just the area. Look at the formula for the weight. It's simply the multiplication of the height times the width. Width is 0.01 over there. Okay, and then levers are still the same. Levers, distance to that point C. Well, I put point C here. Okay, that's fine. And then we'll compute the moments, added them together, and that's the answer. Okay, let me copy. Okay, so what do we do now? Well, it's really uncomplicated because the story is almost the same. I just need to start by changing. I need a circle here, so that's not complicated. This is my function, so it will be the function that we just defined. So it is simply 1 minus square root of 1 minus x squared. Okay. Yeah, okay, that's okay. We start with -1. Okay. Right. Okay, it's a circle. Well, let me just erase this. We don't need it. Okay. So that's my circle. As you can see, this is the computation we just carried out by integration. Result is here through approximation and computation. So you don't really need it. It's accurate enough, even though probably I probably could do better if I added a decimal. Okay. Okay, so that's what we have. As I said, so this is still entirely horizontal. We are computing in a horizontal fashion, so that is my function. And what I have here is the total moment with respect to the origin that we picked over here is 0. Okay, so there's really nothing else for us to do. So I'm going to use the same data, and I'm going to carry out the formula that I have over here. Okay, so there will be a weight attached to, or there is a weight attached to each of the locations. Weight attached to each of the location, which is uniform fortune. So there is nothing about densities here anymore. And then I have to multiply by these levers. Will not be with respect to x anymore. So these are with respect to x. So I can probably mark it here. Not with respect to x, but rather with respect to the y-axis. So lever the distance to the y-axis. Okay, so where is it? Okay, levers to y-axis. Okay, so well, we don't care about that anymore because we care about the distance to the x-axis. But what is the distance to the x-axis? So if I have a point over here, well, the distance to, if I have a point here, well, suppose I have a piece of, if I have a mass over here, located over here, then the mass is, say, whatever, depending on the size, but what is the lever relative to the x-axis? Relative to the y-axis, it's the horizontal. That's the way we did. Relative to the y-axis. So this is what we did. And what were they? They were simply, well, they were, look at it. The formula is simply, as you can see, it's just the distance from the from that location to C. Let me put a different C here, so we would. I don't know what happened here. I don't think I did anything. Okay, so let me. Last time we did put 4 here, so as you can see, that's what we've got. Okay, so so relative relative to 4. Why did I pick 4? Let's pick something else. So 0.5. 0.5. Okay, so so in other words, if I pick 0.5, which is here somewhere, and then I'm looking at what is the its total moment is. The total moment is negative 0.78, which means that it's going to tip. It's going to tip to what? Which way? Support is right here where my arrow is. My mouse is right here. Which way it's going to tip? So 0.5. This is 0 somewhere here, and so I'm putting it halfway through. So this I'm trying to put support here somewhere. Will it stand? Will it balance? Of course not. Which way it's going to tip? It's going to tip left, right? Well, because there are more stuff to the left, and we can see it from the algebra because the moment. This is still the moment the way we computed it previously. It is relative to the y-axis, and it is negative. So that's why it means that there is more negative stuff than positive stuff as far as the 0.5 is concerned. If I put 0, then we'll have 0. Okay, so the answer is the distance to the lever is the coordinate. Always, not the coordinate. The difference between the coordinate and the point. Okay, so but we are doing it differently now. Let me put D here. Say also 0.5. Okay. So so that is that D. Remember, D is the x-axis, the y-axis. So it's here somewhere over here. That's my D. Okay. So we're going to be computing not the we're not going to be computing the levers relative to the y-axis. Now we're going to be computing here levers to x-axis. Okay, for each of the locations. Okay, so what is it, do you think? Let me put a line here to separate. I just have too many things happening. So coordinates, heights. Okay, weights, not weights. Okay, so we're starting a new thing, and now we're talking about our, well, I didn't actually put it right. I'm sorry about that. So levels to x equals c. That's what it is. X equals c. That vertical line, x equals c, with respect to which we're trying to balance, and we did. Okay, so that's fine. Now, now we're doing lever to line y equal d. Okay, so y equal d. So okay, so then the lever is the distance, right? It's simply the distance to d. D in the algebraic sense, but it's actually not that obvious. So I'm looking at each of these bars separately. What is the lever of the bar? So suppose I pick this bar over here. What is it? One bar, say the leftmost bar. I'm out of time. So we have to figure out what the lever is for this particular. It's not a single object. It's whole ball. Okay, we'll just finish it next time.